Let's see from others, people who have done that reading. Is it? Okay, we'll come to it. Anybody else? Okay, so I'll explain, then maybe you can add, Arpan, if there is anything in you want to. So basically, anytime when you're doing the classification algorithm, you do not predict the classes right away. What you predict is probabilities. So I'll give you an example. Yeah. So since the screen is shared now, so when you do any sort of classes prediction, you do not do the actual classes prediction, right? So what you do is so let's say, and we'll be doing this next time around, or maybe today, depending on the time. So let's say we are building a model for predicting who survived the Titanic crash. So survival versus non-survival, right? These are the two classes. Everybody agrees. So either you're going to be surviving or you're not going to be surviving. So it's a classification problem. So when we look into any sort of classification algorithm like a logistic regression model, and let's say there was a person called James, male, age 56, boarded the ship from Southampton, right? All the different parameters. Once you do a classification on this, it will be coming out with two different probabilities. The classification algorithm will be coming out. So it will be saying what is the probability of survival and what is the probability of non-survival. So the probability of survival is, let's say, 0.64. Probability of non-survival will be 0.36. Hence, this person will be classified as a survival with the default threshold of 50% in the binary classes. And we can change that later on. But right now, keep in mind that it doesn't do a prediction of the class itself. It will say James has a 64% probability of surviving, whereas 36% probability of non-surviving. And because of the threshold that we're using, James will be classified as a survival. Is this clear? Right. So that's what the classification algorithms do. They will ascertain a certain probability. Now, in case of iris flower, for example, what do you think this may look like? So you have setosa, you have versicolor, then you have virginica. So it'll say maybe you have 0.67 probability of being a setosa, 0.1% probability of being this, and then the remaining is virginica. So you'll be classified as a setosa flower. Is that clear? So it basically comes out with the probability. And using that probability, then we'll be saying, okay, my default for this probability is 0.33. So as long as you have a higher threshold than 0.33, you will belong to that class. All good, right? So the logistic regression model is not necessarily a regression model, but it's a classification model, but we do certain transformation to make it a regression model. So if you look into the probability and how the probability behaves, it behaves like this, right? So probability cannot be more than 1 and probability cannot be less than 0. Probability cannot be negative. So there's a 0 probability of something happening. It will not happen. There's a 100% probability of something happening. Examples. Probability of 100%, probability of 0%. Sunrise. Till we are alive, there's a 100% probability that sun will rise tomorrow in the east, right? There's a 0% probability sunrise in the west or north or south, unless there's some major transformation that we even don't know, right? So that's where it is, right? And there's a probability in between as well. So what is the probability of rain in Bangalore today? Maybe 10%, right? So there's like 90% chance it will not rain, 10% chance it will rain. So we'll make the probability prediction. But what will happen if we use a linear regression model to make the probability prediction? Right. So linear regression model, by the very nature of the assumptions that we have, they are a straight line. So it will not know that the probability has to be cut off at 1 or the probability has to be cut off at 0. So it will continue to go down and it will continue to go more than 1. So that's why you don't really use a linear regression model to predict the probability. Otherwise, you can say, okay, why do I need to use a logistic regression model, right? I can just use a linear regression model and predict the probability. You'll be right for this range up to a certain extent, but these are all absurd numbers. So that will basically make your model wrong, right? So that's why we don't use it. So like the probability behaves like, this is a typical sigmoid or S-shaped curve for certain event to be happening, right? So let's say we are looking at the GRE score or like the CAT score, and what is the probability of you getting the admission. So if your score is really bad, as the score rises, your probability rises very, very less. And then it has a linear relationship. This is where the linear regression may work in this range, where it's a linear thing. But then again, if you've got a very good phenomenal score, let's say 99.9% in JE, right, versus 99.992%, your odds of getting admission in any school doesn't really change, right? I mean, you are already there, right? So then probability of that event happening does not change and it tapers off to 1, right? There's no further rise. So that's where this linear regression model doesn't come in. So what we do is for shapes like this, which is, typical sigmoid, and most of the events follow this sort of curve for certain probability, right? Let's say your CIBIL score will follow the same thing. If your CIBIL score is really pathetic, let's say 300 or 500 or whatever, right? Doesn't matter whether your CIBIL score is 510 or 540 or 560, you will still not get a loan, right? And let's say you hit somewhere around 700. As your score goes linearly higher, your probability of getting the loan gets higher and higher. And then let's say as you hit, I don't know, let's say you hit 780 CIBIL. Now, whether it's a 780 or 785 or 790, the lenders really do not care so much, right? I mean, you are already an excellent borrower and then you'll get the loan, right? So most of the things will follow this sort of curve in real world, right? So what the logistic regression does very cleverly to bypass this tapering, which is cannot go below 0, cannot go below 1 of the probability, is it does this transformation called a logit transformation. And I will ask you upon anything that I miss, you can add on, right? So it does this transformation, which is a natural log of P. Remember the probability of event happening divided by 1 minus P, the probability of the event not to be happening. And it's called odds ratio. Right? So what are the odds of something happening is also odds ratio in the words of the gambler, right? What are the odds of this happening or betting, for example, right? So P, the probability of event to be happening, divided by 1 minus P, the probability of it not to be happening, take a natural log of that. And when you take a natural log of that, basically when you transform this same sigmoid curve, so remember earlier sigmoid was looking like this. Now the sigmoid changes into this straight line because of this transformation. So this function is a linear function. It can go any value negative, any value positive. The moment I got this linear line, I said, okay, I know what to do with this linear line. I can build a linear regression model, right? So now, instead of me building a probability prediction, I do a prediction of logit. This is nothing but your logit. And this is nothing but your linear regression line, right? So if you remember, this is a linear reg, but we're not doing the prediction of the probability using a linear reg. We are doing a natural transformation using the odds ratio and doing a logit of this. And that's why it's called a logistic regression. But ultimately what comes out from this is a probability that we're predicting, right? Without violating any of the probability condition that it cannot go below 0, cannot go above 1 and all of those things. So that's all taken care of. And that's why it's called the logistic regression. And then once you get this Y defined, and once you get these X's defined, then you can go and build this model. That's what basically the crux of the logistic regression is. You want to add anything?
So same thing. So as for strategy for observe and inventory, this logistic regression came before machine learning invented. So still people are doing probability prediction using logistic regression, not the classification things. So here in logistic, for example, in any regression analysis, what I told, we are expecting average of conditional y given x. X here, in case of logistic regression, y comes with a binomial distribution. So it is 0, 1. So if we do that, if we implement that, there's a formula, we can came like, it will be like P of expected y slash y, it would be the probability of y equals 1 given that x.
Yeah.
So based on x input variable, what is the probability of y equal to 1? So same thing, that is equal to B0, beta 0, beta 1, whatever equation you have told. In case of logistic regression, we cannot, we don't directly model this, because if we directly model this, we'll get a value above 10, above 1 or below 0. So
That's right.
use logic here.
That's right.
So if we use logic, then it will be minus infinity to plus infinity, that value. So that is again linear regression. So it will, we can display that as a line. So now convert, we are having line now. So now in case of logistic regression, we need the probability. We are actually calculating the probability. So still many places we calculate instead of classification, we calculate the probability of some occurrence. So logic, we are on top of the logic, we'll apply sigmoid at sigmoid activation function. It will give value between 0 to 1. At means it will give the probability.
Yes.
So till now, and it all this satisfies regression, because here also in regression also we find the relationship, we create relationship between coefficient and targets. Here also we are doing relationship between coefficient and target. And in regression, target is continuous variable. Here also, if we are finding probability, it is a continuous variable. Now, to decide in the decision stage in machine learning, why we are calling it, because from statistics perspective, it is still a regression. But for machine learning perspective, in the decision section, when you are deciding something, we find some threshold. Based on the threshold, we give the classification. For example, if marks is below 30%, we classify it as a fail. If marks is above 30%, we classify that as a pass. So classification comes in that stage. But before that, in core area, it is still a regression. I read.
Okay, that's good. That's good. Okay, so with that background, we'll move on, and then we'll just quickly give a walkthrough, and maybe one more time we will do a read through of the classification report, and then you can start to build your own model, right? So this is again article number 31, and you can go through some of the same process that you've done multiple times now. So this is familiar to everyone, right? So what we're doing over here, train test split, right? Just like linear regression, no differences at all. Instead of calling in the linear regression, now I'm calling in logistic regression. But we all know that logistic regression is not a regression, it's a classification problem, right?
It's like linear regression. We have fit. Inside fit, we use gradient descent optimization to update the coefficient and to reduce the cost function. But in case of logistic regression, cost function will be binary loss. So cost function will be different.
That's right, log loss, yeah.
Log loss.
Yeah. We'll discuss all of that, yeah. So we'll just call in the logistic regression model, right? We are doing the train again. So far, no difference from the linear regression. The only thing that is different is just the instead of linear and the logistic regression, right? Coefficients and everything work out the same, no difference at all so far. And then we'll look into all of them later on. I'm just saying, we're fitting the model without any hyperparameter optimization. So then we are doing the predict. Again, no difference from a linear regression, same thing. Now, when you do the predict, it will do the prediction and it will automatically generate the classes for you. But underlying, it has done the probability computation. So when you do this exercise, you will see that. And then this is where the major difference comes in. So we will not be using the mean square error or mean absolute error because it's not a regression model. It's a classification model. So when you're looking at the classification model, you'll be looking into something called as a classification report, right? So if you look into this right here, and this is where your confusion matrix, all the things are coming in, and this is your actual, this is your predicted. And these are not the predicted probability, these are the classes. It has automatically converted those thresholds or those probabilities using the default threshold of 50% into the classes, right? So, and then you get this nice confusion metric that we have spoken about earlier on, right? So without doing any computation, you get this report coming out from there. And then I'll also take you down over here, which is the ROCR. We'll discuss that maybe later on. Then this is important, which is the confusion matrix. Remember the cat and dog example we're looking at? So we will say matrix dot confusion matrix, your actual and your predicted, and it will generate this confusion matrix, right? So, and it is, so you can see it is flipped compared to what I had earlier. So in mine, reality was this, model was this, and this reality is this, model is this. So I hope you're able to now connect the dot. But this confusion matrix, along with this confusion, the classification report, gives you all the information that you really require, right? So let's just do a quick walkthrough of this one more time for everyone's information. We'll not do and compute all of them, but at least some of them so that you're clear, and then you can start to work on your. Okay, never mind. I'll just delete this. Okay, so who can tell me the math for the accuracy over here? So remember this table is generated from this confusion matrix. Tell me the math for the accuracy.
Divide all the values.
So let's look into this. So this is true 0. This is true 1. Or you're looking at the reality. This is predicted 0 or predicted 1. These are the predicted values. Clear so far? So how many true zeros we have overall? 1149 plus 145. And that will be this number. Clear? How many true ones we have? This plus this, and that will be this number. And if you add up these two numbers, that's the overall number of the observations that we have, right? Clear so far? How many of those are correctly predicted? Let's do the boxes.
235. Two negative, two positive.
So true and predicted 0, they're matching. So this is the actual true negative. And then this one, this is actual true positive. So the accuracy is nothing but 1149 plus 235 divided by 1758. Can somebody do the math and confirm whether this is this number or not? 1149 plus 235 divided by 1758.
Eight.
78, right? So this is the number that is there, right? So that's good. We'll do one more so that you are clear. Who can tell me the math for 0.83? Precision for 0. What will be the numerator here? What will be the denominator? Let's see if people are agreeing. So I want a numerator and denominator. 1149 divided by 1149 plus
One-
145?
Yeah, 140.
145. Is that correct, people? How many of you agree, disagree?
Two positive plus one plus one.
Hmm.
Two positive plus 1149. Not,
Hmm.
not 235. It should be 235.
It should be 235. So this is not that. This is 229. I think still not clear to majority of you. But is this correct math or no? Can you do the math and correct? Hmm? So remember, the precision works on the axis of the model's prediction. So what is the model predicting? I'm doing a precision for 0. Precision for the class 0 is how many times model predicted that it's 0? 1149 plus 229. 1149 plus 229. And how many times the model was indeed right? 1149 times. So the precision is nothing but this. Is this clear? All good? Okay. Tell me the numerator and denominator for this guy. 235 numerator. Hmm. 235 plus 145. How many you agree, disagree? Double 29.
235. Reality may is with the total. It's difficult to recall.
229. How many of you agree, disagree with this?
Positive and false. 229. Yeah,
229?
correct. 229.
229 is correct, right? So let's see why. Recall works on the actual reality axis, right? So I'm computing the recall of 1. So recall of 1, I'll be going this way. Recall of 1. How many total ones we have? 464. It's basically this number. How many total ones we have? Survivals or the defaulters, whatever you want to call them over here, is 464. How many of those were correctly detected by your model? 235. So the correct math is this one. All good? And we'll keep on revisiting, but this is like the holy grail. So, you must be really very, very familiar with this. And then AUC. So let's talk about the AUC, which is the like the area under the curve, right? And I don't use that too often, but there are like, use cases where you have to be using them. So AUC is nothing but, I think we'll have to go back to the classification report. It's part of the receiver operating characteristic curve or the ROC. And ROC is nothing but you plot your false positive rate and you have your true positive rate over here. And the area under the curve is nothing but this AUC. This diagonal line itself is 50% AUC. So if your model gives you 50% AUC, it is a really bad model. Why? Because if I don't do any classification at all, I just use the normal chance. I'm following this diagonal line, which is the by chance, 50-50. So what does it mean really? False positive rate and true positive rate. So as you are trying to improve your true positive detection, your false positive detection is also going higher. For a random case, they will go hand in hand. So that's why you're going to be in a diagonal. For a good model, your true positive rate will go up sharply without compromising on the false positive rate. So your good model say, okay, I'm able to detect all of the true positives very, very well, right? So what will be an excellent model looking like? Without having any false positive, you're able to detect all the true positives, right? And then you just basically flatten out. So then the AUC will be, who can tell me the AUC, perfect AUC? If the curve is like this, yeah, everything is here, area under the curve, right? Remember, the default AUC itself is 50%. So you cannot go below 50%. You cannot build, I mean, I don't know, maybe you can build even worse model than this, right? So like this, if your model is going like this, right? So then your area under curve can go below 50%. But why would you have that model? Because that's worse than the random, right? So your random model, which is no model at all, will also have AUC of 50%, right? So what does it mean? Really, that if I want to be having a true positive rate of 40%, it says because you're doing things randomly, your false positive rate is also going to be 40%, right? Versus if I build a really fantastic model, I can say my true positive rate goes up, boom, like, I mean, 100% without compromising on the false positive rate, right? So the only caveat over here is that ROC chart or AUC is applicable only for a binary classification. Only works for a binary classification, right? So if somebody says, why don't we use it for like multinomial classification? Because like it's just very well defined for the binary. It doesn't really scale for the multinomial classification. That's why I'm not a big fan of that. But there are like, competitions and hackathons where they'll say, come in and give me the highest AUC, right? Or the best ROC curve that you're looking at, right? And ROC becomes a very good thing for doing a comparative study. So for example, let's say I build a model and model one is coming out like this, red model, model one, right? Of course, the blue model is there. And then I have another model. So let's call this guy as the model 3, right? And the blue model is nothing but your model 2. Which is the best model? Model 3. Why? Because area under the curve is the highest there, right? So area under the curve for the green model is this, right? So that's why this is the best model. So it becomes a good comparative view to take a look at the model 1, model 2, model 3 and see how you're trading off between the TPR and the FPR, which is sensitivity and specificity as well. Some people call it, right? So some technical terms that you can use as well. But those are the main things. So accuracy number is for layman, not for you. Do not harp on the accuracy number. And accuracy doesn't mean anything, right? Accuracy is just like a very, very vague term. Like you're very accurate. What does it mean you're very accurate? Right? So you have to be defining that, like, what exactly it means. So for regression, accuracy doesn't mean anything at all. For regression, you'll be talking about the errors, MAE, MSE, RMSE, right? Or something of similar nature. So for regression, there's no concept of accuracy at all. For classification, even though there's a concept of the accuracy, you are better off using what terms? Precision, recall, F1 score, up to a certain extent, AUC maybe, or ROC. And then last comes the accuracy in the pecking order, right? So these two are interchangeable. This is the F score, basically what makes it like, balanced, right? Since we're talking about this, let me give you some sense also, because you may ask, how do I trade off, right? So going back to this Excel file, there's going to be a cost for you to do a wrong classification. So if you do a right classification, you're good. So this is what? This is right or wrong? This is right. No problem, right? How about this? This is also right. So we are fine. There's no cost associated with this, right? There's a cost associated with this. What is this one? Who can tell me? Are you sure? This is false negative. This is false negative. And what about this guy? False.
That is false negative. This is false positive. This is for one. This is for zero.
So this is predicted as 0. In reality, it is 1. So 1 is a positive.
Positive. So true one is false positive. That is 145 is negative. Positive. Yes, that is 145 is false negative. 145 is negative.
Are you sure?
Yes. Yes. Based on that, we calculated. Yes.
No, we did. We never use the false positive true negative definition, right? So let's just go on one more time. I'm gonna use a different color so everybody can visualize that. So this is the, sorry, this is gonna be too bright. This is the reality. Don't get confused. This is the reality. This is the predicted. Reality is this axis. Which axis are we looking at? This is reality. Predicted is this axis, right? So what is this now? Let's begin here.
Negative.
True negative. Everybody agrees? 0, 0, negative, true negative. How about this guy?
False, true positive.
True positive. Now let's come to this. So what is the reality?
False.
Reality, it's a negative. What is the model predicting? Positive. So this is a false positive. Everybody's with me? How about this? Reality says positive. The model predicted as negative. So this is a true negative. I hope everybody's with me now. Sorry, false negative. False negative. Yeah. Is that clear? That's what I clarified very beginning that, I mean, this axis is going to be flipped in the actual confusion matrix, right? So I just wanted you guys to be more confused than what you already are from the confusion matrix. So that's why I flipped it, right? So this is false negative. In reality, what happens is, let's say, I mean, let's say we are looking at the advertisement campaign. I have built a model for some advertising agency out there. They asked me to see, if I send out this pamphlet, who are the people who are gonna respond to my offer, right? So, or if I give like this sachet, for example, like they send out these campaigns, right? They will send out some shampoo or something like that, or they will say, okay, send this 100 rupees voucher. Can they send 100 rupees voucher to everybody out there? How many people we have? $1.5 billion they will burn right away, or 1.5 billion times 100, right? So 150, 15 billion rupees they will burn right away. So if they send it out to all the population out there, right? So they cannot. So they're going to be very selective to who they send out the vouchers to maximize the odd for them to respond, right? Yeah. So what will be a false negative in that case? What will be a false negative in that case? What will be a true positive? Let's begin there. What will be a true positive? That your model says if you send them 100 rupees voucher, they will buy your product, right? So these are your true positive. These are your buyers, right? So your model says if you send out 100 rupees voucher to these guys and you spend some money sending the offer and all of that, then you have identified a real buyer, which is great. How about these guys? True negative? They are non-buyers, right? So no matter what you send them, they will not buy your product. So why are you wasting your time and effort sending, mailing, this, that? In the US, this is very important because they keep on sending these letters and like very nice pamphlets and all of those things, right? There's a shipping cost, there's a printing cost and all of those things. We're a very digital economy, but there's still a lot of things come in by the snail mail, which is a typical mail, right? So you have to print a nice, you are pre-approved for a credit card, and then you're going through the pamphlet and all of those things. So there's a cost associated with that, right? I mean, $5, $10. So why would you send to somebody who has zero probability of responding to you, right? So this is also good. What is a false negative?
The model predicted they are non-buyers.
Yeah, so these are the people who would have taken your product, but your model says do not send them, right? So these are, yeah, these are your false negatives. So let's say for each buyer that we missed out, I am losing on average $500. So there's a loss of $500, right? In that campaign, if I don't send that offer to those people. So these are the people who are really the buyers of my product. If we have given them this campaign, they would have responded and I would have made $500, right? Because of this false negative, model says do not send them because they will not respond to your offer. I did not send them. I'm losing $500 of loss over here, right? What is a false positive? Hmm?
Model predicts they will buy, but they are actually not. They're not.
Model predicts that they will buy and they are non-buyers. So let's say my mailing cost is $10, for example. So all I am losing on this population is $10. Everybody sees this. The worst I've done is, I mean, I've printed this and sent those to those people. So I'm losing $10. Now you can do the math, like, which of this false positive, false negative, true positive, true negative is gonna burn a big hole in your pocket, right? So then which of this parameter they should try to control and try to lower? So they should try to lower down because every time you're doing a false negative, you're losing $500. Every time you're doing a false positive, you're losing $10, right? So I can actually let some of this population shift to this by optimizing the precision and the recall and all of those things to get this one higher. So I want to have a higher what? How will I get this number to go higher?
That
Hmm?
you might send the offers or something.
Mm-hmm.
The actual who are not who didn't receive the offers,
Mm-hmm.
say we need to send them, assuming that they will buy. So that category might buy, and the conversion rate may be.
Okay.
Send it to positive and false negative.
Yeah. So, but what does it really mean in terms of the precision recall? If we have to go and make this number better.
Stop sending the offers to those who won't buy,
Huh.
and start sending the offers who might buy.
Mm-hmm.
Because and then the conversion rate will be more. If you are sending offers to those who are not converting, you're just spending $10 and losing some of the uh, customers who might convert to the buy the offer.
Mm-hmm.
So we need to stop sending those who won't buy, and we need to start sending who can buy, who might
Okay.
buy.
So let me put it, I mean, I think this dollar number might be confusing, but I think that's good. So let me just put this way. So if I want to have, right, right. So let's say from your 464, who are your real buyers, how many we are able to detect correctly? Who can do the math? 235 and predicted buyers basically plus 145, right? So these are the ones that you're looking at, but in reality there are only 235 who are there, right? So what you're trying to say is from this pool I have to get my this number bumped up, right? Or the like the re hmm? Exactly. So from all the buyers out there, how do I get my recall rate higher? So this will basically translate into, how do you make your recall better than your precision, right? What will you lose with a low precision? Low precision, it says, low precision is basically this one. So let's say if the precision is low on this, it will say these are the people who are going to buy, right? But a lot of them will not be buyer. That's okay. I will lose $10, right? I mean, for the non-buyers. But if I miss out on the recall, that if from the potential recall, like, I mean, people who can buy my product, if I miss out on half of them, then I'm losing $500. So recall basically becomes a better metric for you to optimize from that dollar number, right? So that's how you look into the business problem. It's not a statistical problem. So if somebody says, how are you going to optimize your precision recall? You should ask, what is the cost associated with the wrong decision, right? If I make a wrong decision, what is gonna be a more costly thing for us? Now can we think about any other situation where precision will be more important? Where precision is gonna be really important for the model? Hmm?
This is
Disease prediction, okay, yeah, tell me.
For coronavirus, like where it described and where it might not be right.
Hmm.
It will decide lies.
Right. So it may not be able to detect all of the people out there. For example, I mean, let me just make a even more simple thing. Let's say guilty, not guilty. We are in the court now. Guilty, not guilty. Right? Can the court really claim that I can do 100% detection of the all the people who are doing like some sort of offense out there? No. Right? I mean, there are a lot of people who've done so many bad things and they're walking free. But if somebody comes to the court and they are to be punished or they have to be let go, right? That's where the court needs to be very, very high precision. So if the court says zero, that means you're not guilty. So that means the court has to have very high confidence when it says not guilty, the person is indeed not guilty. Similarly, when the court says guilty, right? There is also a very, very bad cost associated with that as well. That, I mean, if you say guilty and the person is not guilty, he already did 25 years and then you realize, no, by the way, sorry, you are innocent, right? So it's already 25 years wasted from their life. So they need to be having very high level of precision. So I hope that gives you some context, right? And you can keep on pondering. So if you like think over it, you become more clear. And this is not the last time we're going to look into this matrix. So you'll be looking at it over and over again, but very vital for majority of different things because MSc, MAE, they are very clear, no brainer. This is where people get confused, which one I have to prioritize and how I have to prioritize and all of those things. So that's where this really will come in for you to get more context. So with that, you want to use the next 20 minutes to start working on the Titanic data and build, and let's see who gets the highest recall for survival and what is your number. So let's see who claims the highest recall for the survival in the Titanic model. All of you can build it now. Any doubts? What will change in the 6-step process? What are the 6 steps? Let me see first of all. What is the first step? Hmm? After data cleaning and everything, what is the first step? Hmm? No, like the modeling. You have X and Y's. No difference, right? Then second step. Hmm? Yeah, so then you are doing your split. So X train and X test. And then you're also doing simultaneously the scaling. Clear? Third step. No, that is all done. I'm saying in the modeling, actual modeling. What is the third step then? Hmm? We already split X test. We have already done the scaling. Then we are doing the model initialization. So we'll call the log. So this is going to be a different step, right? So instead of the linear regression, you will call in the logistic regression. The third step is the creating the instance of the model. The fourth step, then you'll do the fit of the model. No difference with the linear regression because this instance is different. Same process will apply, right? Fifth step, predict. No difference from a linear regression. Same step will continue. And then sixth step, eval. And this is going to be different as well. Instead of the MAE, you'll be calling it the confusion matrix and classification. And let's see who comes out fastest with the recall for the survival. Yeah, use whatever you want to use. But you have to explain. Mm, 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 mm. So today's assignment for the 10 marks is your linear regression output with your comments, all the things that you've done in the class. You can still work on it and submit later on for 10 marks. Linear regression for today. For next class, we'll decide. It's going to be a combination of the logistic regression and a decision tree. You've already created the LMS for the submission. Yeah. Yeah, it's okay. You want to modify something, you can otherwise.
We can do.
What is the date? We can make it till Wednesday. Okay. Anyone has the number? 0.91 for Titanic. That's a really good number. Let's see if others can also validate. How did you do this? I mean, any customization or just fitting of the model? We'll check with others. Recall for 1 for the. So you're saying recall for 0. Then it makes sense. Then it makes sense. Hmm. Hmm. And
I got recall accuracy 77,
Hmm.
precision 72,
Hmm.
recall 73.7.
for class 1
Yes.
or overall?
Overall.
Overall. Okay. Anybody else? Okay. So when we come back in the next class, we will see how to make recall better. So right now there is a recall that you've got, right? So how to make it better, or how to make any metric better by doing something called as a threshold optimization, right? So that's going to be the flow for the next time, threshold optimization. And you should read decision tree ensemble like we have done earlier on, right? Random forest, and also read KNN and something called as a cross validation. So we'll try to cover all of this. And once we cover the cross validation, then we'll come back to something that we left off in the linear regression, which is the lasso, ridge, and elastic net, right? We'll come back to it after we have done the cross validation discussion. So that's going to be the flow. Threshold optimization, hyperparameter optimization, cross validation, decision tree, random forest scaling, and then go back to the linear regression, which is the lasso ridge and elastic net. Yeah. On that note, shall we wrap it up? Any final questions, comments?
Assignment, linear.
Linear, just polish and submit that. So we've already done that. So if you're comfortable what you have done, then you don't have to work on it. If you want to modify that and resubmit it, you can.
When
By Wednesday. By coming Wednesday, you can submit or resubmit your linear regression model. Yeah. Okay. Thank you, everyone. Take care. Your device.
The first day, which we use for
Which one was it?
first the Titanic one.
Titanic.
Please save that notebook.
So I'll do that.
Whatever you have completed.
Uh-huh. I thought I already shared. No, Titanic one is not shared.
That is the before solving. Before discuss.
Okay.
After discussing.
Okay.
You've done some change there. I want to see it.
Okay.
Just needed one small answer.
Ah.
I had not submitted one of the assignments.
From where?